In the near future, robots will encounter us more and more in everyday life. Besides tasks that the robot can solve autonomously, there are also many interactions with a human being. One of these tasks is the transfer of objects between robot and human. This results in close contact between man and robot, which can cause insecurity or anxiety, especially among inexperienced people. In order to increase the feeling of safety, we have developed and tested a movement model that is based on the movements of humans. The imitation of human movements is a well-known method for improving the feeling of safety. Models for human-like transfers developed so far focus primarily on a human-like trajectory. However, this can lead to inhuman robot poses. Like these. That is why we have developed a model that is oriented on the joints and not on the pose of the end effector. The path poses are thus in the joint space and not in the Cartesian space. In order to determine joint movements, we analyzed visual data from 2 studies. In these studies 2 people handed over an object. With the help of various analyses, movement functions for the different joints were developed. During the analysis and development, we noticed 2 different variants. In the first variant, the elbow moves continuously into the target position. In the second variant, a more pronounced flexion of the elbow, at the beginning of the movement, requires an additional extension at the end of the movement. The variant can have different degrees of intensity. After the analysis, we transferred the movements to 2 robots, a humanoid pepper robot, and a Kukuyubot arm. In order to test the performance and the sense of safety, we then carried out another study. We asked 15 participants to take a look at the robots. All participants were secretly divided into 2 groups. 10 people formed the experimental group. The remaining 5 are the control group. The study was divided into 2 phases, to see whether the subjects could perceive a difference in the movements. In phase 1, the subjects were not informed about the details of the experiment. Both groups were shown 2 movements of each robot, the humanoid robot and the traditional industrial manipulator. The movements were different for the groups. The experimental group was shown a human-like and a non-human-like movement. However, the control group was shown the non-humanoid movement twice per robot. The first phase was followed by a questionnaire survey. Questions regarding the recognition of differences and human similarity had to be answered. Afterwards, an explanation was given to the test persons. They were informed that they were shown 2 different movements and that one of them is more human-like. There was no explanation of what the differences are, nor what the more human-like movement is. In phase 2 the movements for both robots were shown again. The different movements for the experimental group and the same movements for the control group. The questionnaire was then repeated, with an additional question regarding the feeling of safety. The statistical analysis of the data of the study shows different results. Details can be found in the paper. In summary, the subjects were able to perceive the difference between the movements. This was already clearly achieved in phase 1 of the industrial robot. With the humanoid robot, the subjects only noticed the difference in phase 2, after the explanation. This is probably due to the small difference between the motion models of the humanoid robot. The control group ruled out that this change was based only on the explanation. In comparison, it can be seen that our joint movement model is regarded as more human-like. Here too, the difference is clearer for the industrial arm. Our model also performs better in terms of safety. Further results are presented in the paper.